If you haven't done so yet, make sure that you pause the video and just reread the problem in order to reacquaint yourself with it before listening on. Our goal right now is to find the force on the charge located at x equals 8 centimeters in figure A, and they are giving us that Q is equal to 1 microcoulomb. Let's zoom in on the picture of part A so we can get a better understanding of what's going on. Now again, we want the force on the charge located at x is equal to 8 centimeters. So the charge that's located at x equals 8 centimeters is this charge right here, the one marked negative 2q. So we're looking for the overall net force acting on that charge. And to begin doing that, we're going to want to label our charges. So when you have a problem like this, make sure that you label each of your charges. For example, we can call the charge on the left side Q1, the charge on the right side could be Q2, and then the charge in the middle could be Q3. Next, what we want to do is draw the electrostatic forces that are acting on charge 3. We only need to draw the forces acting on charge 3 because that's what the question is asking us to do, is to figure out the net force on that particular charge. So consider the fact that Q3 is negative for a moment, and then the fact that Q1 is positive. Now, because they are oppositely charged, they're going to create an attractive electrostatic force. So in other words, Q1 is going to attract Q3 towards it. So we would have an attractive electrostatic force tugging Q3 to the left towards Q1, and we could label that force F13. That notation simply means the force that charge 1 is exerting on charge 3. Now, similarly, Q2 is positively charged. And since Q2 is positive and Q3 is negative, they are opposite in charge, and therefore another attractive electrostatic force develops. And this time it's going to be pointing to the right because Q2 is attracting Q3 to the right. Now you might notice that Q2 is closer to Q3, so its electrostatic force is actually going to be larger. So we're going to draw a larger force vector, and we're going to label that F23. That would represent the force that charge 2 exerts on charge 3. So those are the two electrostatic forces acting on Q3. And we can see that they are oppositely directed. So when we go to calculate the net force on Q3, we're going to make sure that because F23 points to the right, that we call that a positive electrostatic force, and F13 points to the left, so that would be a negative electrostatic force, so F13. Now what we're going to do is use Coulomb's law to develop expressions for each of those two electrostatic forces. So for example, for F23, we're going to take the Coulomb's constant K, and then we're going to multiply that by the magnitude of charge 2, and multiply that by the magnitude of charge 3. Notice we're including those charges in absolute value symbols, so that even if a charge were negative, we would be evaluating the positive version of that charge. So we'll see that momentarily. And then we're going to divide that by the distance between charges 2 and 3 squared. Don't forget to square that distance. And then we're going to subtract a similar looking expression. Again, using Coulomb's law, we're going to have the Coulomb's constant multiplied by the magnitude of charge 1, multiplied by the magnitude of charge 3, and then that's going to be divided by the distance between charges 1 and 3 squared. So at this point, we might want to pause and just make sure we understand those distances. So let's take a small aside here. Let's figure out the distance between charges 2 and 3. Now take a look at the diagram, pause the video, see if you can figure out what the distance between charges 2 and 3 would be. Each of these tick marks represents 1 centimeter. So if we're measuring the distance between charges 2 and 3, we would just count the tick marks. So here's charge 2. We're just going to count the number of ticks to get to charge 3. So it's 1, 2, 3 tick marks. That's 3 centimeters, but we need meters. So take that 3 centimeters and divide by 100, and you get 0.03 meters. Similarly, we're going to find the distance between charges 1 and 3. And we just count the tick marks. So it's going to be 1, 2, 3, 4, 5 tick marks. That's 5 centimeters or 0.05 meters. So we're going to now begin plugging in the values. Let's take a look at some others. We know that Q1 was equal to positive Q. Q2 is also equal to positive Q. And then Q3 is equal to negative 2Q. So we're going to take all of these values here and we're going to plug them into the equation that we have been developing. So there is our setup. Now, again, notice that we have absolute value symbols around the charges. So when you look at the absolute value of negative 2q, you can actually just end up writing that as a positive 2q because you're taking the absolute value. And then the same thing here. We're going to rewrite that as a positive 2q. Now we can continue simplifying this expression because if we look in the numerator, we're multiplying a 2q by a 1q, so that's going to be 2q squared. And then the same thing over here, 2q times q is a 2q squared. So we're going to rewrite those numerators next. Now what's interesting is that the numerators are identical. They are both 2q squared multiplied by k. So you can actually factor it out. You don't need to do this, but it makes the calculation a little bit easier. So if you factor a 2q squared k out of the expression, you're going to be left with a 1 in each of those numerators. So we would have 1 over that first distance squared minus 1 over that second distance squared. So that kind of simplifies the calculation. At this stage, we're going to be plugging in the final values. We were told in the question that Q had a value of 1 microcoulomb, but we want a standard unit of coulombs. So to change that into coulombs, you just multiply by 10 to the negative 6th because micro is 10 to the negative 6 as a prefix. So that's your value of Q, and then K is the Coulomb constant. It's often written as 9 times 10 to the power of 9, and then the funky unit of that is a Newton meter squared per Coulomb squared. So that's what we're going to plug in for K, and also for Q, we've got that 1 times 10 to the minus 6. So let's go ahead and plug in. And when you carefully evaluate that on your calculator, you should get a net force acting on charge 3 equal to 12.8 newtons. Now notice it came out positive 12.8 newtons, and that means that the overall net force is acting to the right on Q3. And that's sort of what we predicted, because when we look back at the drawings of the force vectors, we made F23 a larger force vector relative to F13. So we had already anticipated that the net force would turn out to be positive because that vector pointing to the right is larger than the vector pointing to the left. So again, the final net force is 12.8 newtons.